All right, part 3 of chapter 13 on magnetically coupled circuits. Today we're going to complete the chapter talking about probably the most common form of magnetically coupled circuits, and that is transformers. Um, so let's get right to it. With linear transformers, here's an example of one, and it's deliberately chosen to be, the most natural dot convention. Here are the dots up here, both nice and clear at the top, right here and here, of course. And we just want to write two simple loop equations with a load and a voltage source and a series resistance. These, of course, can all be generalized in the future to impedances and such. So let's write the loop equations, and we're going to write them in the frequency domain. So here is our input loop, right? Quite simply, the voltage is the resistance R1 plus J. So this is factored. Here's the two elements dependent on I1, right? And here we've got the one element dependent on I2 in the first loop, right? Piece coming back. On the second loop, which is the one that is going to help us. So in the second loop, we've got no voltage source is equal to, and now we just need to pay attention. If I2 is flowing this way through L2, that means this side is positive. And so when I1 flows through this way, it is making the dot side positive. So when I do the mutual coupling, it's going to connect dot to dot. And so that will be in opposition to the voltage created across L2 by the current I2. So we end up with the minus sign here. This was true in the first equation, but here it is again. And then R2 plus j omega L2 plus whatever the current is across the load. So those are all positive because they're all in the same direction of I2. This is negative because the two currents oppose each other. All right. The input impedance now is, of course, the voltage across the input up here, right, divided by the current that flows out. And this is going to create, right, we just simply start solving the equations. And the easiest way to do this is do our solution of the second equation, right? The minus sign gives us very nicely j omega m times I1 is equal to I2 times this whole thing, R2 plus j omega L2 plus Z of the load. Okay, so then I1 is equal to this whole thing, I2 times R2 plus j omega L2 plus ZL over j omega m. Okay? And if we then take this value and plug it back in here, take this and plug it back into this equation, or we might have preferred to solve it the other way. Actually, that looks like it would have been best right now to solve for I2 as a function of I1, right? That would have been a lot easier, would have been j omega m over this whole thing, right? This R2 plus j omega L2 plus ZL, right? And then plug that into here. Probably would have been a smoother form, but you can recognize the elements. Here is if I did that substitution, here is this term, minus j omega m times I2, and that's gonna give us this, right? Because we're gonna get j squared omega squared m squared minus that, and of course this whole thing is going to become positive. So that's going to give us this nice term here on the end. And then the front end term is very simply this divided by I1, right? So kind of straightforward there. This is called reflected impedance, right? It's how the whole load transformer and everything looks to anything way back here at the input, right? Zn is back here. It's how everything looks looking in here, right? This is a common move to make. And so you can look at the reflected impedance then is this portion back here. The total impedance will be the Zn. This portion, this portion down here, you now recognize, is the reflected. Okay, so there's that, and we always have that going on. This, by the way, I'll give you an event. The last chapter we're going to study at the end of the semester is called two-port networks, and you're going to see actually in this a sense of these very networks and taking elements like a transformer and other things and turning them into just boxes that have terminals on them. And a step in that direction is this right now. Here's a transformer, and the transformer only. Notice there's no source or load, but it is designated as we're used to and sort of like seeing it here with the dots up top and so forth. So if we write now, let's assume there's a V1. We're just using the labels that are here. Looking in from this side, the loop equation here, written in basically all we're doing is taking the equations that we had before without the input impedance, right? Notice up here there's no input impedance up here, and there's no R on the second side over here. So this is the raw simple equations. Where am I here? This is the raw simple equations in matrix form of that input loop. Let's take one. V1 is equal to j omega L1 times I1, right? Plus, notice how the currents are now. I1 and I2 are going into the dots at the top. So this will be plus j omega m I2. Okay? And the same is expressed for the second one. So now we have them in simple matrix form. It might also be handy to place them in I as a function of V. So this is, right, the inverse. The inverse of this. Okay, and you remember inverse, here you can recognize this term at the bottom, right here, is the determinant, in case you've, right? And then we find each of the individuals, right? We switch these two, and we switch this with this, right? We switch these two, and then we put minus signs on these two, and that's how we find our individual element values here in the determinant. Then you can see that we've switched. Here you can see we've switched the bottom one, so we got L2 up here and L1 down here. And then these two, M was the same. We actually switched them, but the important thing is we added a minus sign, right? So that gives us an inverse, and we're going to want that because of the equivalent circuit that we're going to make. So one of those, the first of two equivalent circuits, is called the T equivalent. And we call it that simply because when we lay it out, it looks like a T. So notice here in the equivalent circuit idea, the four values, V1, I1, I2, and V2, are the same and the same orientation as up here in the original transformer circuit. Okay, only now we're going to call it an emulation if you want. It's not really an emulation or a simulation. It's just saying if I wanted to make that transformer circuit up out of elements like this, just simple inductors, what would it look like if I connected them in a T shape? Obviously, what we're going to do here is we're going to find, what are we going to do? We're going to find the same matrix form. We're going to find the same matrix form of the mesh equations. And then we're just going to match up terms, right? So if I do that here they are. For this, pretty easy to write over here, right? If I got this current, I've got I1 times LA, J omega LA, and I've got I1 times J omega LC. I've also got, because L2 is coming down here, J omega 2 LC, right? So pretty easy to see these terms and these terms. Similarly, on the back side, I got J omega LC times I1, right? That's the contribution over here. This J omega I1 LC, right? Same way. And you can see that. So now if you compare terms, it is pretty easy. If I compare, I'm over here in my equivalent circuit. I now compare this term to this term. And that would mean what? That L1 is equal to LA plus LC. And if I do that with all of them, I get this, right? And the important thing then is I get over to, I don't want to miss this step. This last one, LC, is just simply, right? LC is simply equal to M. And then I can go back and substitute over here and solve for my LAs, my LB, C, and M. Right? All simple substitution. So I get the T equivalent circuit, which is a substitute. If I wanted to unplug the full dotted model or the full dotted picture of the transformer, I can substitute the T equivalent. Another way to hook them up is in the shape of a pi. We call this the pi equivalent. These, by the way, are common pictures that we're going to be encountering later when we make equivalent circuits. So the pi equivalent now is this, and we're looking, notice again, the same variables apply in the same direction at the terminals. All right, and this one, if we do this as currents, so what are we going to be doing? We're going to be using this form of Ohm's law, V over Z, right, and find currents everywhere. And if we fill out the matrix, this is what we're going to get. Obviously, on the I1 side, I1 is going to be equal to this current plus this current, right? And so as a component. And so anyway, if I follow through all this, I'm going to end up with 1 over J omega LA times V1 plus 1 over J omega LC times V1, right? So maybe we're going to want to write this out. LC experiences V1 on this side and V2 on this side. So there's a net voltage here of V1 minus V2. Okay, and that is what gives us, or gives rise to, this term and this term, right? Those are directly a function of that V1 minus V2, right? 1 over j omega LC times V1 minus V2. Anyway, we go on and write all of those. So now we have this form of the equations. And here are, I bring over the one. This is our advance. So this is from our, one is from our equivalent circuit. And this set is from our transformer circuit. Okay, and now all we have to do is match them up term for term. Once again, we can match this up with this, right? We can match this up with this term and so on. All right, and when we do that, do all the math, the plugging and chugging and grinding around, we will get this, that LA is now L1, L2 minus m squared. And you can kind of see this coming, right? Here's 1 over LA there's that denominator, but it's the inverse. So now that's going to end up on top when I actually solve for LA. And the L2 minus m is going to float to the bottom because there's going to be 2 terms there. Okay, and you can follow that math through, but it's pretty much just matching up elements between the inverse equation and the straightforward equations out of the pi equivalent circuit. That technique, by the way, is something that is going to be repeated over and over again with the notion of equivalent circuits, which turns out to be a very powerful analysis technique in electrical engineering, but also just in modeling in general. And modeling is a big deal, whether it's electronics, electrical work, or mechanical work, or civil work. Making models, mathematical models, is important. This is a good encounter with it. All right, so let's try this practice problem. You have some examples there in the text, but let's do this one. So we can find the input impedance, right? We know is to be, we want what's looking here. So we have a Z in, and we know there's going to be a primary part, which is 4 plus J8, plus a reflected part, right, which is going to be omega squared m squared, I'll just write it this way first, over what? The output impedance, which would be, we can say we've got R of the output plus J of it minus or plus whatever load we've got. I go over here, by the way, to keep this easy and looking like the past. I'm going to combine this with this into something that's minus J2. And this guy will be our R2. Okay, so it looks like the inverses from before. So we will have 6 plus J10, and then what? Minus J2, this is the load, right? Z of the, I'm calling that Z of the load. Okay, and so this gives us, what? This gives us 4 plus J8 plus our omega squared, or omega m is 3, right? Omega m is 3. So this gives us 9 over 6 and J10 minus J2 plus J8. All right. So if we do all of this math, which we will here, we're going to get what? 4. We can do this quickly. 4 plus J8 times 6 plus j8 plus 9 over 6 plus j8. Okay? And so if we do the math quickly, we got 4 times 6 is 24. Then the j squared times 8 squared is going to be minus 64. Minus 64. Then j8 times 6 is j24 or j48. And then let's see, I lost track. I'm sorry, 4 times j8 is plus j32. All right, plus 9. All over this bottom, 6 plus j8. So this comes to something nice like minus 31, right? 24 minus 64, so that's minus 40. So minus 31 plus j80, it looks like, over 6 plus j8. All right, so now it's just a matter of reducing this. And if you do, we can get the steps. The top portion becomes 85.8 if you do this in phasors. I mean, you can do it as complex math if you want, that's all right. And the bottom is 8 and 6 is something about 10 at 53. Okay, and so this comes out to 8.58 at an angle of 58.05 degrees. Okay, which I see is what they have here. All right, and the current from the voltage source. Well, that we can find directly. We have the voltage, so the current is going to be the voltage, that's our 40 at an angle of 0 degrees, and we're going to divide that by the Z, 8.58 at an angle of 58.05. And we're very hopeful here because this is going to end up a minus sign, and 40 divided by 8, there's my pen, so 40 divided by 8 is 5. It's going to be something just under 5. So I think we're good here with this number. Okay? All right, I think we have time for another practice problem in here, and let's just do the next one, the pi equivalent. Okay? And this is really just chasing down the values. I think this is pretty much just plug into formulas, right? We have our formulas for the pi values, right? And that is, okay, the pi values are LA is equal to, I'm just copying here, L1, L2 minus, so whoops, L1, L2 minus m squared over this nice determinant piece, L2 minus m, L2 minus m. So let's just plug and chug. That's pretty much all this is. And that's the beauty of the equivalent circuits. The T, in some cases, the T is a much easier circuit, right? So L1, L2 is 40 minus m squared. That's 2. And we're talking henries now, right? This is not omega L or omega m. So that's 4 over L2, which is 4 minus m, which is 2. So what does this come to? It's our 40 minus 4 looks like, whoops, 36 over 2 is 18. Okay, So this is pretty much just plug and chug, and I think I'll leave it at that and save the time for later. We know this LC is going to end up the same, and the mid one, you can plug in the values for that, but it's pretty much just in that formulas in the text. All right, and a final one here with, so this will give you a lot to work with, plus the examples in the text. We're going to use the T model to calculate the phasor currents I1 and I2. Right, so we're going to have this picture when we're done. Right, and then we'll attach over here 12 ohms, and over here our voltage source of 12 at 0. Right, so this will be LA. So this one will be LA is equal to what, our L1 minus M, and that is going to be what, J5 minus J3, so that's J2. Okay, so I'll let you find all of those. I'm just going to write in some values here, J2, J3, and J3. These are the nice easy ones to find. And we've got I1, right, like this, and I2 like that. Okay, just copied them off the picture. All right, so now I'm going to write the mesh equations and keep that easy. And they will be 12 is equal to what, I1 times minus J4. Ooh, I forgot to put that guy in there. Up here. Where am I at? I lost me. Here I am. Whoa. Right here. Minus J4. All right. So I1 is minus J4, right, plus J2. That from the model. So here's the input added capacitance, and then here's the model piece, plus J2. All right. And then it's going to be plus, what, J3, the middle bar, times the current in there, which is I1 minus I2. Okay? And just to speed it along, I'm going to pull all this together and call this JI1 minus J3 I2. Okay, I just gathered all the terms. The second equation is 0 times what, J3 now times the same quantity, I1 minus I2, minus J3 times I2. Right, so this is the upper bar of the T, that's the shared bar. But then we also have the resistor in there, so that's minus 12 I2. And we'll pull all this together as what? J3 I1 minus I2 times 12 plus J6. Okay, that's minus 12 minus J3 times it, pulling out the minus. Okay, so we're good. Those are two good equations. So now we can take the second. So from the second equation, right, we're going to get J1, Ji1 is equal to, things get a little dicey here, 1/3 of I2 times 12 plus J6. And I kind of did this eyeballing that 12 plus J6 was divisible by 3. So I2 times what? 4 plus J2. That's the relationship between those two. Right, so if I substitute, where's my pen? So now substitute into the first, right, and I get 12 equals I2 times 4 plus J2, right? That's the I1 equals this, right? So we get that right away. Minus J3 times I2, right? So I went in, just so we're not lost, I went into this and substituted my JI1, right? So that's J3 times, what do I have here? J3, or I made a small 3 like it's a subscript. J3 times I2, right? So I went straight away for that. And I just plugged my JI1 equals I2 plus 4. Plug that straight in here for this first term. And then I've still got to add my minus J3 I2. Okay, and if I then solve this, first of all, collect the terms for I2. This is I2 times 4 minus J, right? Pretty easy here. 4 and minus J3 plus J2 minus J. All right, and that's equal to, I'm just going to convert that to phasor, 4.12 at an angle of minus 14 degrees. It's probably 14 and some change degrees, but that's it. So then I2 is equal to what? 12 divided by this thing. 12 divided by hang on, this is I2 times, I just converted this to the phasor. Okay, so then I2 is going to be this divided by 4.12 at an angle of minus 14 degrees. And so that leaves me with something, what, a little smaller than 3, in fact 2.91 at an angle of plus 14 degrees. Okay, so that's the current I2, and we did get that. So I1, obviously you just plug it back into our relationship, which we had right here. We could put all this back together. That I1 is that, so I1 is going to be this. Where am I at here? The 2.91 at an angle of 14 degrees. Times 4 plus J2. All right, so I plugged in for I2, and then I'm going to divide all that by J. Whole lot of fiddling and fooling around there. But when you do the math, you come out with, you got 2.91, and 4 by 2 is going to be, what, 16 plus 4 is 20, so the square root of 20 is going to be a little over 4. So this number should be just a tad over 12, right? So I'm gonna estimate this as 12 plus plus, and I can probably take a guess at the angle, but at any rate, it's going to be 14 plus something 2 by 4 is probably something about 25 degrees. And then the j in the denominator is a minus j on top, so that's going to be minus 90 degrees, something like that. Okay, so I would expect something in the range of 12 plus plus at an angle of 14 and 23 is 2737. So what, about 43, 44 degrees? Maybe one of these is bigger, I don't know. I'm going to say about, it's not 45 degrees, but I don't know, 43 degrees. So we got a number here, 1349. I think if you do the math sharply, it'll come out right. Okay, so that's some practice problems there. Now we're going to move on to ideal transformers. All right, so now we're talking about ideal transformers. And by the way, in doing this, we're not really talking about a small subset of transformers. Most transformers are ideal. They have very good coupling, so the coupling coefficient is considered to be 1. That's part of what ideal means, and it turns out that's a whole lot of examples. We've got, I'm just bringing back the frequency domain equations that we saw before. We had these in matrix form, but we've also had them in this form. And I'm just going to solve here for I1 in the first equation, right? So I1 from the first equation, right? I'm taking this thing down here. I1 is going to be equal to V1 minus j omega m I2 over j omega L1. Okay, and if I plug that into, now take this result, I'm going to do what I usually do and put it back in for that guy, right? I'm going to get this. Okay, so here let's just check all the terms. We've got V2 is equal to j omega m times this. So here's our j omega, canceling that j omega, and m over L1. So there's here's V1 j omega, canceling that. So it's V1 is, here's this term, right? Then we've got j omega m, right? Over j omega L1. So here's this term has become this term, or vice versa. And then we tag along this last term is here, right? So everything's accounted for. Okay, and if we now go, we know, right? We know that for m is equal to what? K times the square root of L1, L2. But for k equals 1, this is the square root of L1, L2. So that's the first invocation here of something that's ideal. Right, k equals 1. All right, so we have that. So now let's take a look. We've plugged that in. Here's our V2. And all I've done, or the book has done, is plugged in for m this value, right? And here's m squared. Ooh, right there. That's m squared, and that's plugged in for m. Okay, and the rest is just observing now. This m squared becomes what? L1, L1 over L1, so that cancels. So this term becomes minus j omega L2 I2, which exactly matches this with the opposite sign. So those two terms go away. And this is left with what? Square root of L2 over L1 V1, right? Because this canceled with one of these. All right, fancy way of writing it. And that is, oh, hey, there's the number of turns ratio showing up, right, which we like very much. So look at, in ideal cases, this is important. The two voltages, input and output, relate to the turns ratio. And so you could be, depending upon which way the ratio goes, as a fraction or a larger number, you can be stepping up or you can be stepping down. All right, and we like that idea. So a transformer is ideal when, let me just summarize as the book does, when the coils have very large reactances, right, and that drives M to infinity. The coupling is unity, all right, and we can get that a lot with iron cores. If you look at any real transformers, household Bell transformers, any significant transformers, they're wound on iron cores with tightly coupled coils. And the primary and secondary coils, these we're adding, weren't really discussed, but the primary and secondary coil, these resistances that we're so used to including and are there when you have things wound on paper cores or their air cores, that sort of thing. The coils are lossless, thought to be considered to be lossless. All right, here's an example of that. The book has nicely shaded all this material in here so that it really looks like iron, right? This will be an iron core or something very, very high permeability. But it has two turns, N1 and N2, and that's the turns ratio. This is the picture. And we do like to include, so those are number of turns. This is often stated, sometimes it's more likely stated as just a turns ratio, or more likely just a voltage ratio, voltage out versus voltage in, and from that you find the turns ratio. So you don't know the literal number of turns unless you go in and do a little more measurement and exploration. Typically, this double bar in the middle is an indication that you have an iron core. It's not an exclusive indicator, but it's very commonly used, and it means high coupling. You know, pretty much it means iron. All right. Now Faraday tells us that the voltage on the first side, we've seen this before, is the number of turns times the time change in flux, right? Same is true on the outside, the number of turns times the time change in flux. All right, the turns ratio is the output to the input, the ratio of those two, just a definition, okay? So in phasors, we just say we've got the phasor voltages and the number of turns, right? It could be listed either way. You can list these right here. It's kind of listed as time variables, and here it's phasors. Okay. All right. So now we've got this ideal transformer, and we're putting it in a simple circuit. We're going to put a power supply on the front end and an impedance load on the second. Now notice in terms of our typical indications, we're back to saying I2 flows out. That would be something that flows like this, like we're used to writing in our meshes. And now we're indicating turns ratios here instead of impedances, right? So it's going to be all the same circuit, but the givens are more like what we talk about for ideal transformers. What we do know is that the power in is equal to the power out. Okay? And in phasors, we can say that the turns ratio is what? The direct proportion of the input current to the output current. Inverse proportion of the output voltage to the input voltage. Okay? And so simple relationships, if the turns ratio, transformers are generally talked about as voltage transformers, step up or step down. And what they mean is the voltage is stepping up or stepping down. So when you're talking about currents, you need to think of it the opposite way. And that's because the power, where are we here? Whoa. The power in is equal to the power out. So if I'm stepping up the voltage, I've got to be stepping down the current. Okay? 4 possibilities exist, just like they did before, all based on the dot conventions, right? So here we are with the first. I'll just put them out because you can look at them in a straightforward way. When the dots are in probably the most popular or candid, desirable location, they're on the top, and the currents are specified flowing in and flowing out, right? So this arrangement is typically how we like to think, right? It's the popular approach. I apply a source on the left, right? I put a source in here, and I have my output over here. Okay, and the current flows out to it at some voltage. So that's probably going to make it the most popular. If you turn it around, the currents turn around. That's all that happens if you turn the current indicator around. And the other two are the obvious ones, where you've got the dots changing on each side, and then the dots changing and the currents changing. So you just have to be careful, as you always have. But the first one on the far left here is the most typical. And with nothing said, that's the one that's usually assumed. Okay? So in summary, you can just follow the rules stated in the book. If V1 and 2 are both positive or both negative at the dotted terminals, use positive N. Otherwise, use minus N, right? And what are they saying? Positive N is just this thing here. Oh, this thing where? Right here. This is N. Okay. And if I1 and I2 are both enter or both leave, use minus N, right? So that picks this case and this case are both enter, so use minus N, right? Otherwise, use plus N. Okay? Simple rules, I guess, to remember. To be honest with you, I always carefully work it out with my fingers and a pencil. Okay, so let me just take these obvious voltage current relationships right here. And we just want to find a few things about reflected impedance, these sorts of things. Basic relationships that we're going to be able to enjoy. So power in has to be power out. So in phasor form, right here we are on the input side. Notice the conjugate. And that's just simply plugging the values from above, V2 times N, over N times I2 conjugate. All right, and the N's cancel, and we get this, right? So the product of the voltage times the conjugate current on each side yields the power there. All right, what about the impedance? It's V1 over I1, right? And that is simply taking the first two, making the product of these two, written like that. And the second two are the product there. So this same cancellation thing is going to go on up here, right? Whoops, where's my pen? Here we are. To give us this, we've got the N over N, so it's going to be V2 over Ni2, so 1 over N squared. So what happens here here is what you might call some output impedance, right? Something like that. And it reflects in as 1 over n squared, right? A little more powerful. So the output, or the load, right? Any load attached comes across, when we had that in the picture on the previous slide, as over n squared. All right. Now, we want to eliminate the transformer for analysis, all right? And this doesn't necessarily mean plugging in a T or pi equivalent, though that could be a step. What we want to get to, here is our transformer, right, and we're just analyzing it in the generalized form, where we've got, some loads or some impedances with sources on both sides. And one of these sources could be a load, okay? All right, now this goes to this, where we take a Thevenin voltage on the input, whoops, and we have the output remains the same, so we're just taking that step. All right, the Thevenin voltage is V1, and that's V2 over N. Why? Because we've got a simple reflection coming in, right? It's V2 now. Let me just point out, don't get confused. This is V2, this is V1, right? This over here is something else, VS2. All right, we're claiming now that that's VS2. The only way that can be true is if I1 is 0, right? Otherwise, you'd have a drop on the load. Okay. Then if we apply a unitary voltage, not bad for analysis, on the input, right, we're examining this picture, and we get that the Thevenin impedance at the input, right? So where are we looking? We're back here. Whoa, whoa, whoa. We're right here. Thevenin, right? That's where we're looking. It's V1 over I1, where V1 remains the source over there. And so now we're just plugging and chugging in the usual way, expressing it in terms of I2, right? So you can see what we're headed for here. This is the input expressed as the output. And so that's Z2 over N squared. You see the N over N, but then V2 over I2 is Z2, right? There's that Ohm's law relationship. Okay, we're just analyzing it with a simple. So now if that's the circuit, right, we're saying the reflected values on the input side, here's our reflected, right, Z load reflected. And here is the V on the output reflected. So now this is a nice single loop, but notice we're still identifying V1 right here between points A and B. Okay, what has been lost are points C and D, right? Kind of a circuit equivalent thing. So the reflected secondary to the primary is what we're looking at here. The same process can be used with a unit source on the output or the secondary side. And we can go through all that analysis and reflect the primary into the secondary, right? And as you would expect or hope, here we've got N squared. So primary impedances reflected to the secondary, well, I was going to say increase, but N might be a fraction, right, if it's a step up or a step down. So this will be taken care of in that fact. Just like here, if N is a fraction, Z2 will actually come across as an increase. A fraction would be if it's a step down. Okay? So the transformer can be eliminated through reflecting the output impedances and the output source values, if there are any. The opposite side source values, primary to secondary, secondary to primary. Okay, let's try this out in some practice problems. All right, so we have an ideal transformer, and 2200 to 110. So 2200 to 110. I'm going to right away do this. This will make 20. So we're looking at 20 to 1 is how I tend to think of it. 20 to 1. And this looks like step down, right? So n might be 1/20th, right, or 0.05. All right, and then we want to know the kVA rating. Okay, so if it's rated at 5 amps at the output, all right, 5 amps at the output is, what have we got? N is, all right, so the kVA, oh, by the way, this up here looks like I copied a different problem. So this is 25 amps in the 6th edition. All right, so then we've got, so at 25 amps, that's I1, right? And I2 over I1 is what? 1 over N is equal to 20 I1. Okay, is equal to 20. So 20 I1 is equal to I2. Cross this out. Okay, so that means we had a step down. So now we have I2 is equal to 20 times this, or a whopping 500 amps. Okay, remember, power is the same on both sides of the transformer. So when we stepped down by 20, the current stepped up by 20, which was a big deal. Okay, so the complex power, whoops, let's stay here. The power is V1 I1 conjugate, but that's also V2 I2 conjugate. Okay, so take it either way. And you've got what? On the input side, you got 2200 times 25, which is going to be 55 kVA. Okay, so this is 5 times what we had before, so we're going to expect this to be 500. And we've already found the secondary current, so here we have it. Let's just check. Of course, it's going to work because we only divided by n, or multiplied by n. So what did I do here? This is the input side. Okay, on the input. And the output side, the power, is going to be what? 110 volts, but times a whopping 500 amps. All right, and so that's quite easily put down 3 zeros and then a 55. Okay, volt amps. All right. We'll do another here, problem 13.8, where we've got this. We want to find V out, of course, the amount on the load and the complex power. So pretty much going to come down to, the difficult part is going to be finding V out, because to do that, we're going to have to find the currents. And of course, when we have the currents, the power will be relatively straightforward. All right, so let's note the dots and the current. Notice the problem picked to make them opposite. All right, so I'm just going to jot down a couple of relationships here so we've got them. V2 over V1 will be minus, remember because the dots are opposite, N2 over N1. Currents are in opposite direction relative to the primary, and so is I2 over I1. Right, that's going to be minus what? The reciprocal, N1 over N2. And our little n, which is the ratio of the two, we can say is 4. Whoops. The output side, 4 to 1. I'm looking at this right here. It's 4 to 1. Okay? So we have those things in front of us. Let's reflect the secondary to the input side. We want to find V0, but basically it's a problem of solving for the currents. Right? So we're going to want to end up with this little picture. Right? Here's our 2 ohms. And we're going to want to end up with, if we do that little knobby thing, there's our reflected output. And, right, we'll go back to this. So this in here is this load, 16 minus J24. Right, so where we've got this thing is 16 minus J24 over what? 16. 4 squared. Okay, n is 4, output to input. All right. So the Z Thevenin then, the Z Thevenin, we just basically have to collect all these terms, right? So the Z Thevenin is equal to 2, that's what's there in the first place, plus 16 divided by 16, looks like 1, minus J 1.5. Okay? So that's 3 minus J 1.5. And I'm just going to go ahead and put that in phasor form. 3.35 at an angle of 2657. Oh, and it's minus, so it'll be minus 2657 degrees. Okay, that's our Z. The I1, that's our Z Thevenin, right? So now it's easily I1 is our input source, 240 at an angle of 0 degrees, divided by Z Thevenin. So this is 240 at 0 divided by 3.35 at minus 26.57. So the input current is let me find that number, 7164. 240 divided by 3, it's going to be something a little less than 80, right? And the angle will be 2657. Okay, so that'll be I1. We can follow this quite easily with I2 equal to, right? We have this as a simple turns ratio, minus 1 over n times I1 at this point. See, isn't this nice about the transformers? With that ideal coupling and the assumptions made about it, it really makes it easier to move things back and forth. So I2 is what? 7164 divided by 4 minus this, minus this at an angle of 26.57. Okay, So if I clear that all out, well, we can just leave it for right now, except this will be 4 into 80, some number a little bit less than 20. So it's going to be minus 1791. I used a calculator at 2657. Okay, which we'd expect the phase current there to be the same. Okay, so that's I1 and I2. It looks like, which have we got? Minus, yeah, we can switch this. The minus sign here can be put in here. That just swings it out, swings it around 180 degrees, right? So we're good with this. Whoops, where are we here? We're good with that current. I'm not sure they got kVA is the wrong notions on there. Oh, we want complex power. Sorry, we're not done. We're not done. All right, so 1791 is the current. All right. Now the output voltage. Let's get over here where we've got some fresh paper. The output voltage is going to be, what have we got? We're back to the original circuit, right? We need the output voltage right here. So that original circuit is minus J24 times I2. So more math, 24 at an angle of minus 90 times 1791. And you can do the minus if you want, but I'm going to go with minus 153. So I did a 180 degree inversion there. 0.93. All right. And that comes out to 429. Right, you can see that 24 times about 18, 429.8 at an angle of 116.57 degrees. Hopefully, well, that's looking possible. Look, here is that current right here. Pretty close. Okay. And you can see that was sort of coming with this 26 plus 90 from the J24. You're going to end up with something around 116, getting that all straight. And finally, the power supplied by the source, right? The power supplied is what? V1, I1. So that is our 240 times I1, which is 7164, right? And that is well with the angle. I'm sorry. We'll bring the angle back. So that is 17,193 at an angle of minus 26.57. I just grabbed the angle from over here. It was the complex value, right? The complex value of this. All right. So that's I think that's all we'll do for the ideal transformer. With auto transformers, the real difference is that everything is on a single winding. You can see this. You can see this even in the schematic. Here's the iron core, as always. You can imagine a single coil like this, and notice the dots are in the same orientation, which they're going to be. The coil is wound in one direction. You're just tapping off of one part. It's as though you just scratched some of the coating off of a coiled wire and soldered a wire in there in that sort. Okay? And this one is a step-down transformer. If there are a total number of N1 plus N2 coils, right, so over here the inside, the primary side is experiencing the sum of those coils. The secondary side is only experiencing N2 of those coils. Okay, so this should be a step down, and you can imagine that just by observation. Fewer coils are intersected on the secondary side. Okay, so it's just the ratio of coils. So notice in the step down, you're going to have 1 plus some number. So you're going to have a bigger number right on the secondary. I mean, a smaller number on the secondary. Power, of course, is conserved. The power on the input, V1 to I1, is the same as the power on the output. Okay. Taking that relationship just reinforces, in another way, the idea that reinforces the idea that the turns ratio for current and voltage are inverted. Okay, and here they are, right? Just as we'd expect. All this is this up here inverted, right? Turn it around. Okay. Physically, you can see, and I do like this about auto transformers. Physically, you can see here we have N1 plus N2 coils on the secondary and N1 coils on the primary side. So this is going to be a step up transformer, right? A little bit of voltage here on the primary. I'm not sure where my pointer is right now, but a little bit of voltage on the primary is magnified on the secondary, right? So V1 is to N1 as V2 is to all the coils. And V1 over V2 is just it's more than the inverse of the ratio, right? It's the difference. You're taking N1 over that sum. But pictorially, it just makes a lot of sense. This is how a step up is going to look. And we can do the same factoring and come to 1 plus N2 over N1. Okay, for the current, that is. All right. All right, so this is practice problem 1310 from the text. And you'll notice it's just a modification of this picture. So I'm going to convert to a pen here. And it says a 2-winding transformer is 60 volt amps, and it's 120 and 10 volts. So this is 120 and 10. All right, so this is 120 down here, right? And so we know our windings ratio, if we need that. And the transformer is 60 volt amps. Okay, so what have we got from this? We have S1, we know the power S on the number 1 side, the input side is 60 volt amps. And that's what? V1, which is our 120, I1. So I1, all this gets us is I1 is 1/2 amp, right? All right. Now S2 also is 60 volt amps, right? S2, 60 volt amps, and that's 10 volts times I2. So I2 is equal to what? 6 amps, right? So the total current, you need to keep track now of where I1 and I2 will be. So where is it? Here's my I1, right? I1. Here's my I2. And this guy right in here is my I total, which will be 6.5 amps. All right, and at 6.5 amps, so now the power on the power from the power rating in the transformer the power rating, is going to be equal to, totally, it's 6.5 amps times the, 120 volt source, right? So that's 720 plus another 60 is 780 volt amps. Okay. Let's try one more here real quickly. This is a step down, so one reason I want to go ahead and do this. The V1 is 2.5 kilovolts. V2 is 1 kilovolt, right? So what can we find right off? Okay, so I'm going to modify this. Sorry, I didn't do this ahead of time. To jive with the text in the 6th edition, V1 is 8 kilovolts and V2 is 2 kilovolts. So with a load of 16 kilowatts, right? The power of the load, the 16 kilowatts of the load is equal to V2 times I2. And we know V2 is 2 kilovolts, right? So I2, 2 kilovolts times I2. So I2 is going to be equal to what? 8 amps. Okay, so now if S2 is 16 kilowatts, that's going to be equal to S1, which is V1 I1. All right, and that means 16 kilowatts divided by V1, which is 8 kilovolts, is equal to I1, and that's 2 amps. Okay? And so if we want to know what I0 is, we're doing a summation, right? I1 plus I0 is equal to I2, according to the diagram. So we just plug in what we know. I0 is equal to I2 minus I1, or 8 minus 2 equals 6 amps. Okay, I think there's a bunch of other example problems. So between that and this, I think we'll call this the conclusion of Chapter 13. We're not going to cover three-phase transformers, and we'll be getting on with the next material.